Okay, let me start by reminding what happened last time. So we consider it, so we showed the following statement that if you have a subspace A in topological space X, which is what we defined to be as a deformation retract, then it gives a particular example of homotopy equivalence. So A, in this case, it follows that A is homotopy equivalence to X. And we consider various examples of deformation retract. And then we consider it the notion of paths in topological space X. And we consider it operations on them. Particularly, there was operation of taking inverse of a path and composition of paths. And we consider it also notion of path homotopy, which is a particular which is a particular case of homotopy with additional restrictions that the endpoints. So it's a homotopy between paths such that also endpoints stay fixed at each value of the homotopy parameter. Okay, and yeah, so we showed how the operations, we proved various properties which show how operations behave under path homotopy. And then we finished by defining the fundamental group. So where we finished last time, so let me write again this definition. So fundamental group of topological space X. So it's denoted by pi1 x comma x0. So we take what is called a base point, some arbitrary fixed point in our topological space. And then the fundamental group is denoted by pi1. It depends on the choice of topological space and a base point inside. And so as a set, is defined by as a set of equivalence classes on a space of all paths. That's it, continuous map from an interval to a topological space X, such that the initial and the terminal point, they coincide with the base point. So that look, the passes here look like this, and we quotient with respect to equivalence relation given by path homotopy. Meaning we can deform this loop. We are allowed to kind of deform this loop such that the along the deformation, this point stays fixed, because both this point, which is both initial and terminal points, always stay fixed. So this gives particular. So this the corresponding quotient gives us some set, but we want more structure in the set. So we want to define a group structure in the set. So we should consider this as a group, and the group structure given essentially by composition of paths, which we defined earlier here in the last lecture. So the group structure is given by, so the elements in the set are homotopy classes, are path homotopy classes of paths. And as usual, these equivalence classes we will denote by, represented by a certain path f, we will denote by square bracket. And we define the group structure by saying that the, if you want to take a product of two classes represented by, one represented by path F and the other represented by path G, F, and this somewhere G, another path which starts and ends at the same base point x0. This is, we define this to be the result of this multiplication. We take to be the equivalence class of the composition of paths. So here, this inside we have a composition, and this is a group operation, group multiplication, which we define essentially as follows. But of course, we want so this requires some additional work. So we have to show that this is actually well defined. Because we define group structure in terms of particular representative, so we need to show that there is this actually, the result is actually independent on the choice of representative. And second, we have to show that this is actually forms a group. So this satisfies group axioms. So that this definition actually makes sense. Okay, so remark. So we have to make two remarks. So first remark is that this operation, just as an operation between from a group times a group to itself, is well defined. Namely, independent of the choice of representatives. F and G. The result of multiplication should only depend on equivalence classes, but not on the choice of representative. And so suppose, so how do we check this? So indeed, let's take a different representative, some other representative, a couple of a pair of other representatives. So we take some path, another path F prime, which is path homotopic to F, and G prime, which is path homotopic to G. And let's check that the if we use this representative, the result will be the same. Okay, so here we take this another pair of representatives, and we use the definition of multiplication, and this is will be by our definition, this will be a class of the composition of paths F prime and G prime. But last lecture we proved a proposition about various properties, and one of the properties was that this is the composition. The composition of homotopic paths is path homotopic. The composition of homotopic paths are path homotopic. So we know that this is from the proposition from the last lecture. We know that this is path homotopic. So the class, the equivalence classes, indeed should be the same. This works. So the result is the same. So this is well defined. Okay, and the second part remark is that this satisfy the multiplication satisfies group axioms. So what are the group axioms? First, there exists an identity element. So that multiplication by it is trivial. So, and indeed there exists an identity, and this identity is a class, can be defined as a class represented by a constant path. So it's again, it's a path just stays at my base point x0. So this is a constant path. And why this is the identity in our group? Let's see. So if you multiply, if you take arbitrary class represented by some f, and so we use our definition. So we need to compose this f with a constant path. But of course, this is obviously the composition of some path, and a constant path is obviously homotopic to the path itself. So indeed, and analogously, one can check that the multiplication from another side gives us composition of paths in different order, and this is also homotopic to f itself. So the class, the equivalence class, is the same. Principle, if you wish, one can write explicit homotopy, but you can see, I mean, using this kind of prescription, using this technique which we had before, so we just need to homotop. So the composition, if this is a homotopy parameter, and this is a S is a parameter along path, so the composition is, to do the composition, we first split into two halves. Here we have a constant path, and here we have path F. And then the homotopy to f itself is just given by rescaling f, this 1/2 interval to the whole interval once we change t from 0 to 1. And we map everything in this small triangle to just x0. But it's intuitively, it's kind of obvious because if you have a path, you go such that you go along f and then you stay at some point, obviously you can deform this to pass this to the original path. And the second axiom is the existence of the inverse. So for any element of my group, which is represented by, again, by some path f, we should have to show that there exists inverse. So that if we multiply by this inverse from either from left or from right, we should get identity. And indeed, this can be shown by the existing inverse can be shown that this just by taking the inverse to be a class represented by inverse path. Just take like it, and let's check that this indeed satisfies the properties of the inverse. So if you take, so we have to check, for example, if you multiply the inverse from the left, we should get identity, and let's see. So this should be a multiplication of the class of the inverse to f, and the class of f itself. And then we use the definition of the product in our group. So this would be a class of composition of f and f inverse. But then last lecture, the previous lecture, we showed that this is such composition is homotopic to constant path. So this was a part of our proposition. So this should be the same as a class of a constant path, and this is indeed our identity element. And the other way around can be dealt with similarly. So I'm not going to show this. Basically, we have to check that the product in the opposite way is also identity. And finally, we need to show associativity. We need to show that if it, so now we have a triple of group elements, which are represented by a certain triple of paths. So let me say, so the paths which start and end at the same point, they called loops. So there are a triple of loops. And then we have to show that if we take a product of G and A, of classes of G and H, and then multiply by class of F, this is the same as taking the product in a different order. So first we multiply the class of F with the class of G, and then we multiply it with the class of H. So we need to check this. Okay, so let's consider what the left-hand side explicitly. So this is by definition. So first we use the definition of a product here. So this should be the same as the multiplication of a class of F and class of composition of paths G and H. And then this is should be the same as a class of F composed with the composition of G and H in this particular order. And similarly here, this is the same, by repeating essentially the same thing. This is a class of the composition of path F with path G, and then composed with path H in this order. And in principle, these paths, this pair of paths are different in general, but again, in the proposition last lecture, we showed that these compositions are homotopic. Are path homotopic, and this means that the equivalence classes are indeed the same. So the associativity holds. So this finishes the proof that our definition is well defined. So this is indeed gives us. Any questions? So, so we have seen that. So the definition for the definition we want to. So we have a topological space X, and we have to fix a base point. And the fixing of base point. This is because we need this in order to. You can see this because you need in order to kind of compose to define a group structure, you need to compose this loop somehow. And to compose these loops, you need to kind of fix a base point so that you can do this composition. So there is no unambiguous way to consider loops kind of at different places. That's why you need to choose this base point. But this looks like some kind of additional information, but in principle, we would like to have just something like invariant of a topological space itself. But the thing one can show that the dependence on the choice of this base point is pretty mild. So in particular, one can show the following proposition. That if you take for a path connected topological space X, we have, so if we choose, we can choose some other base point, let's say x1, and consider this group, the group defined for another base point, let's say x1. The corresponding fundamental groups, they're actually isomorphic. If you only care about group up to isomorphism, then essentially this is the same group. This is for any pair of points x0, x1 in the path-connected space X. In principle, as you will see from the proof, it's enough to have this isomorphism. It's just enough to require that x0 and x1. So if X is not a path-connected, the same is true just when x0 and x1 are in the same path-connected component. Is there a question? Okay, so let us show this by explicitly constructing the isomorphism. So X is path connected. This means that there exists a path between this pair of points. And let's denote this path. Let's say H. Exists a path H. Again, it's a map from an interval to X, and we want which starts at x0 and terminates at x1. And then we will define the following map between BH, beta, which is known by beta H. And this will be a map between the corresponding fundamental groups. As a fundamental group for this base point, for X with base point x0 to the fundamental group with base point x1. And then, so we will define this map, and then we will show that actually this map is an isomorphism. And again, so we can define. We have to define this map on equivalence classes of loops starting and ending at x0. So we take some class represented by some f. F here. And we want to get a class here. So we want to get a loop starting and ending at x1. And the way to do this is what we can do. We can go in the opposite direction of path H. So we go along H bar, and then we go along F, and then we return along H itself. So what we want to send this loop to a loop H bar composed with F composed with H. And this will be a loop. So this is a loop based at x0, and this is a loop based at x1. Again, here the composition, the order of composition of paths is not important as long as we are taking equivalence class. And okay, so we want to show that this is an isomorphism. So first we want to show that this is a homomorphism. So it respects a group structure, and then we need to show that it has inverse. From it, it will follow that it's necessarily isomorphism. So first, we check that this is a homomorphism. It respects the group structure. Okay, so in order to do this, we need to check that if we take if we first take the so we consider a pair of elements as a group, and so we know that their product is given by the class of F composed with G, and so we need to check that if we act on BH by BH on this element, this will be the same as a product of action of BH on F and on G. So this is so let's see where BH takes this element. And so by definition of BH, this will be taken to H composed with F, composed with G, composed with H bar. And then what one can do is one can, we know that there is we can always insert somewhere a constant path in between. And this means we can insert in between a pair of paths. So we know that the composition of a path with this inverse is homotopic to a constant path, which corresponds to identity in the fundamental group. So we can insert this combination for free, and then indeed, since we consider this element up to homotopy, so this is homotopic to a constant path. Since we consider this element up to homotopy, we can the order of composition of paths is not important. I mean the order of brackets, which we would put here, and so we can rewrite it and put the brackets this way instead. And then we use, so this is yes, so this is so this is this pair, this and this, they are loops based at x1, the loop based at x1, and again, so this is of course the equivalence class of loops based at x1, and this was equivalence class of a loop based at x0, and so then by using the definition of the group structure in the fundamental group for the base point x1, this is just a product of the corresponding classes G, H bar, but this is the same, so this is action of BH on F, and this is action of BH on G, so this is beta H of F times beta H so indeed so what we showed that the BH of what we showed that the BH of a product is equal to I have to put brackets here because it's classes. So what we showed that the BH of F, class of F times class of G is equal to BH of class of F times BH. So indeed, this is a homomorphism. And now we want to check that this has inverse. And by inverse, we'll check that the inverse is actually beta, but corresponding to, if I swap the role of x0 and x1, I can consider beta h bar as a map from pi1 of x1 to pi1 of capital X x0, right? So just swap the role of x1 and x0, and then h bar, we know that h bar now is a path from x1 to x0. But we need to show that this is the composition of these things is identity. So we need to show that this is composition is identity on pi1 xx1, and similarly the other way around, its identity on pi1 with base point x0. So let's show this. So let's apply to show this. Let's apply this composition to an arbitrary element represented by some loop f. So this is a loop at x1, and well, we first apply beta h bar, and this is by definition is following. So h bar f h following class, and then we apply again beta h using the definition. So this the result will be the following composition. But these pairs, position of these pairs, they are homotropic to again to constant paths at x1. And they act, their classes are identities. In the fundamental group, so this is the same, indeed the same as F. Indeed, this is true, so this is identity, and similarly, I'm not going to show it, but this is absolutely similarly, also beta, the other way around, composition is identity. Pi1 defined for base point x0. Okay, it has both left and right inverse, and since if you have homomorphism which is bijection, we know that this is necessarily isomorphism. So it follows that beta h is an isomorphism. This finishes the proof of the proposition. these groups are isomorphic. So one can make the following remark, that for a path connected logical space X, one can just write pi1 of X, meaning that this is some group defined up to an isomorphism. So usually, if you want to compare two groups, we want to check if they are isomorphic or not. This will be enough. Yeah, this can be enough to distinguish the topological spaces. Any questions? And so a path, if the logical space is path connected, then it is called simply connected. If by definition this fundamental group is trivial. Well, I will denote trivial group here as 1. So this is the definition of a space being simply connected.
Professor, I have a question. Is this equivalent to X is gamma topic to 1-point topology? Namely, this group is trivial group if and only if X is gamma topic to 1-point topology, 1-point topological space, just 1 point.
Well, for a point, it's trivial, but if it's trivial, it's not necessarily a point. Well, we know, for example, that if you take, as we showed, for disk, in disk any mapping into disk is contractible. So in particular, pi1 of a disk is trivial, but disk is not homomorphic to a point. Well, it's homotopic to a point, but there are also example. If you take, for example, a sphere is not a homotopic to a 1-point space, but still for a sphere, the fundamental group is still trivial.
Okay, thank you.
Well, we will address this more carefully later. Why this? But at least kind of individually, you can see that if I take any loop in a sphere, I can always collapse, contract it, deform it to just a trivial point, because any loop on a two-dimensional sphere, I can just shrink it, right, to a point. Any other questions? Okay, so sorry. Okay, let me make a comment on this definition of simply connected. This kind of explains why explains the name. So for X is simply connected, if and only if any two paths are homotopic to each other. Any paths from x0 to x1. So f of 0 equal to g of 0 equals to x0, and f of 1 this can be used actually as a equivalent definition. So if for any pair of paths between a couple of fixed points, so here we fix x0 and x1, and currently the statement of space being simply connected is that any such pair pass homotopic to each other. Well, this can be easily showed. So let me briefly prove this. So suppose we show it first in this direction. So assuming X is simply connected, then any pair of paths between two fixed points are homotopic to each other. Path homotopic. So we are given the fact that the fundamental group is trivial, and we need to show this. And so let's consider the following composition: F with G inverse. So this will be a path which goes first along F and then returns along G bar, so in the opposite direction of G. So this is a loop based at x0. So then it defines, it gives a certain, it's a representative in the fundamental group for base point x0. And so we know that the fundamental group, so it's an element in pi 1 of x is base point x0, but we know that this is trivial. So this can be only, it can only be an identity element, which is a class of a constant loop. This means if they're in the same equivalence class, this means that there exists a path homotopy between this composition and the constant. And so let's start with this, and we can, so this relation, we can compose both sides with G on the left, right? We know that the composition is respected by path homotopy, so we can compose left and right-hand side with G. So we get that this is equivalent with homotopy, it's composition of G and X0. And then, but then we see that this is, we can consider this pair, G and G bar, and this composition is homotopic to a constant loop, which we can remove, and this we can also remove this constant loop. So it follows that G is homotopic to F. Basically, geometrically, the statement that if one can deform this G to F with fixed X0 and X1, this is equivalent to that this composition of F and G bar can be deformed to a constant loop here. Okay, and well, let's show this another way around. Suppose any pair of for any pair F and G pass between X0 and X1, they're homotopic. They pass homotopic. This follows. From this, it follows that the fundamental group is trivial. So now we are given this pair of. So we know that for any pair F and G, they pass homotopic, and so let us take. Let's consider take H some any loop based at X0. So we take some H. This. And then what we want to do is that if you consider the following composition, H and F, so this is will be a pass from X0 to X1, because H takes us from X0 to X0, and F then takes us from X0 to X1. And we know that for any pair of paths from X0 to X1, they should be homotopic to each other. So in particular, we know that this composition should be homotopic to F itself, because F was also a path from X0 to X1. And then, so again, now we start with this, and what we can do, we can multiply both sides with F bar. So we get the following. And then this is, we know that this is homotopic to a constant path. And this is also homotopic to a constant path. And this is homotopic to itself. So this means that H is homotopic to a constant path. And this means that H represents a trivial element in fundamental group with base point at X0. But H was an arbitrary loop, so we showed that the class of arbitrary loop is trivial. So this means the fundamental group is trivial. Any questions about this equivalence of two definition of simply connectedness? Okay, so now we want to calculate some non-trivial example of the fundamental group, and so the the very important example is a fundamental group of a circle, and so here we will consider it's convenient to consider the circle as a quotient of a real line of integers. So we understand the real line. So this so what this means that so the real line set of real numbers, and we declare two real numbers to be equivalent if they differ by some integer. Of course, this is definition. This space is isomorphic to the usual kind of representation of a unit of a circle as a unit circle in a two-dimensional Euclidean space. A subset of points with norm 1. And the explicit isomorphism, if you wish, we can consider explicit isomorphism phi, which sends so that phi of t is the vector cosine sine 2 pi t sine element. And we want to show the following theorem. The fundamental group of S1. So S1 is isomorphic to Z, so a group of integers. Again, if you so this is S1 is path connected. So if you consider this up to isomorphism, we can suppress explicit choice of base point, but we can also choose so if we can also in principle choose a natural base point, well, just in this representation of S1, we choose a class of 0, the quotient, and then one can make a additional statement that this group is generated so the group of integer has a single generator corresponding to 1 here. Well, the trivial element is 0 and generated by a class of a certain loop omega, where omega, so omega is a loop in S1 such that well, it starts and ends at 0, and explicitly it's given by sending t in the interval to just a class of t. Yeah, t may be not a good notation. Let me use s. We usually use s. If circle is like this, right? Well, t, yeah, so it's essentially interval 0, 1 with 1 glued to 0. So the loop omega is just starts at 0, and well, if I use better to do this. 0 is here, so omega is just a path which goes once around the circle. And for the proof will be a bit later. We need some to show some additional proposition before. So simplify the proof. This is just as a motivation for what we're going to do next. Well, again, maybe before it's useful to consider another example, kind of correlation of fundamental groups. So if I mean, there's the following statement: if X is contractible, and the notion of contractible we defined the last time, is that it follows that the fundamental group is trivial. Again, before we showed that if space is contractible, this means that deformation retracts to a point, and so in particular it follows that it's path connected, as we showed before. So how one can show this? So if space is contractible, this means there is a homotopy from F like this, which takes, which is a homotopy between identity on X and a map which sends the whole space. Okay, let me write it like this. And F1 is a constant map which sends any point to some fixed point x0. So this the subspace consisting of this x0 is a deformation retract. And so we will take this point to be a base point, which to which we have a deformation retract to be a base point for a fundamental group. And then if you consider some loop H, at this point, at this base point, x0, we can of course so we can consider the following composition: F. Okay, let me write it here. So let me define a loop HT, where T will at an interval HT. So this will be another loop such that for any T, it starts and ends at x0, and I will just define by the following formula that HT of S is equal to F of H S of T, and we know that H of 0 the same as our H, and H1, replace T to be 1, this F, this is, so for T equals 0, this is identity, and when T equals 1, this is just maps everything to x0. So when T equals 1, this is a constant loop at x0. So our homotopy, which kind of contracts everything to x0, it also contracts this loop to a constant loop at x0. So this means that it follows that so this function as a function of two variables, S and T in the interval provides us, so this means that this is a path homotopy which realizes between H and Cx0. For arbitrary loop, we show that this is homotopic to a constant loop, and this is it follows that the fundamental group is trivial. And we considered examples of contractible spaces to be a disk or Euclidean space. This can be equivalent. Yeah. But of course, so we want, so if space is contractible, the fundamental group is automatically trivial, but the inverse is not true in general. Before calculating fundamental group for a circle, we need to do some preparatory work. In particular, we want to introduce the following definition. It's the definition of a covering space. Of a topological space X. So covering is another topological space. Denote X tilde, which is equipped with the projection, what is called a projection map. P from X tilde to X. So it's a pair we wish it's a pair x tilde and the map P, and the map P is required to satisfy a certain condition such that for any point x in our topological space X, there exists an open neighborhood let's say U containing X such that the following conditions satisfied. Let me split it into pieces, this condition. So first, the condition, if you consider inverse image of this neighborhood of X, this is as a form of a union of open sets alpha, which do not, let's say, label it by indexed by some set, say I, such that they do not intersect for different value of the index. They do not intersect. The disjoint union, essentially, for alpha different from beta basis. And moreover, if I then consider, so this is of course, this is some subspace in X tilde. One considers restriction. So this each of these U alphas is a subset, open subset in X tilde, and if one can restrict our map P on this subset U alpha for some fixed index alpha, and this will be a map from U alpha to U, and this is required to be a homomorphism. The bijection, and it's continuous, and inverse is also continuous. And such subset U in X is called evenly covered. Okay, this looks pretty complicated, but what is the kind of what is the geometric meaning of this? And well, the prototypical example is actually given by what we want. And so consider X to be a circle, and then the role of covering will play R, and our projection, which is a map from R this one will just be projection corresponding to the quotient which we use to define circles. So define a circle as a quotient of R mod Z. So this T is a real number here is sent to the class, its class circle. And why is it evenly? Why is it satisfies these properties? So this is because one kind of way to represent this map P as following. So we consider S1 kind of line, if you wish. All right, imagine there's some sort of three-dimensional plane. This S1 kind of lies in the bottom plane, and then R can be understood as some sort of infinite spiral. Let me try to draw this. This. R, our real line, which we represent like this, so that each we know that each preimage of each point here is some integer, right? So if I take the P inverse of some class of T, this is just a set of real numbers like this, so they differ by all possible integers. So each point here has infinite number of lifts, and this can be understood as the points on this spiral which project, and here the projection is just a projection from this three-dimensional kind of space to this to the plane inside, to the horizontal plane. Okay, and why this condition which we have is satisfied? So let's consider. Essentially, it's enough for this neighborhood. So we take some point X on a circle, and it's enough to take just this U to be any sufficiently small arc. Well, just it should be just not a full circle. It's enough to take an arc which is not a full circle, which contains this point X, and then we can see that the lift the lift will be a disjoint union of intervals in our plane, right? Because if you consider some small neighborhood of X, it will lift to the preimage of it will be a union of small neighborhoods here. So if one can kind of this is U, and this is a union of these intervals, which is obviously disjoint, are U alpha. So here we can choose this set which labels U alphas to be a set of integers. P inverse is of U is a union integers n. And indeed, so okay, they're all disjoint and they're all open. And indeed, if I'm going to just restrict our projection to one of these intervals, on the spiral, this will just provide, this interval is of course, this projection will just provide a homomorphism between this some fixed interval in this collection to the interval on a circle. So, obviously bijection and continuous. Are there any questions about the definition of covering space and in particular this example? If you have questions, it's better to ask now because after this we will have to, there will be some rather complicated proof of a certain proposition about covering spaces. Okay, so we formulate the following proposition. We'll probably finish, yeah, we'll finish the proof only next time, I think. So let us consider certain map so fix a map F. Consider pair of topological spaces Y, X, fix a map from Y times interval to X. So this can be some continuous map which can be assumed as a homotopy between restriction of F at 0 and at 1. And we also fix another map which will denote F0 tilde. It will be a map from Y to X tilde, which is a covering of X with projection P dot X as in definition. And the statement that then there exists a unique map F tilde from Y times interval to the covering space X tilde such that P composed with F tilde is equal to F. And that F, if I restrict F tilde to Y, if I restrict this element in this set to be 0, so I restrict F to Y times 0, this restriction, which is a copy of Y, this restriction coincides with my fixed F0 tilde. So let me a bit elaborate. So there is a on this. So this is what is called that F tilde is a lift of F. So in general, what is the definition of a lift? So here, yeah, I'm not proving yet this is proposition. So let me give you first a definition of a lift. So a map F tilde from Y to X tilde is a lift. It's called a lift of F of a map F from Y to X with respect to map P from X tilde to X. So here, Y, X, and X tilde is in principle just an arbitrary triple of topological spaces. Well, for us, the relevant case will be when P, X tilde is covering, and P is a projection for this covering, but in principle, this can be considered just an arbitrary triple of topological spaces, X, Y, and X tilde with a given map, with a fixed map, some P from X tilde to X, and we also are given a map from Y to X, and so a map of tilde is called a lift if if I compose it with P, this gives me F. So this can be it's convenient to use the following what is called commutative diagrams. So in this to depict what's going on, so we have a map. So we have a fixed map F from Y to X, and we also have a fixed map P from X tilde to X. So this is a pair of given maps, and we ask a question if one can find the map F tilde from Y to X so that this diagram is commutative, which means that if you go this way, this is the same as going this way, and which is exactly means that this composition is equal to F. This equivalently is that there exist F tilde, so this means that this is commutative. I mean, often there for a pair of so such lift may exist or not, and that's why it's often kind of you can denote by dashed arrow. So there is a question. Often one can ask a question if F tilde such that this diagram is commutative exists, may exist and may not for given F and P. And then using these kind of commutative diagrams and the notion of the lift, these propositions then can be all these properties can be depicted using this commutative, using the following commutative diagram. So we have we are given some map from Y times interval to X, which is denoted by F, and we are also given a map P from X tilde to X, and we also can consider an inclusion map of Y into Y times interval just by including a copy of a topological space Y to as y times 0 point here, the inclusion map. And we also given a map f0 tilde, which is a map from y to x tilde. So this is specified, and we know that this is, so it's a given that this commutes, right? So we know that if we compose f0 tilde with p, this is in agreement with the restriction of f to 0 here. So we know that this part is commutative, and then we ask a question if there exists a lift of f. So we know that there exists of restriction of f to 0, but we ask if there exists a lift of the full f. So if there exists such map here, that everything here is commutative. Doesn't matter which way we go, we will get the same result in this diagram of maps. And the statement is positive. The proposition tells us that this f tilde indeed exists and is unique. And this is what we will show the next time. Are there any questions?
No questions.
Okay, that's it then for today.
Professor?
Yes.
Can I ask some question regarding the homework?
Yes.
I mean, like, just want to ask some general direction. So, for example, in the first question in the homework, that to prove that to construct a deformation retraction of a square with deleting one point onto a point, can I just use the fact that a square deleting one point is homeomorphic to a plane by a stereographic projection, and then from a plane we can use the straight line homotopy to retract it into a point? I just want to ask if it can do something. Can I do something like that in the homework?
Yes. Yes.
And for example, other question, do we need to construct explicitly the map, or
no? You just can, if you can just describe it geometrically how it looks, it's enough.
Oh, it's okay, right?
Yeah,
for example,
you don't need to. It's not necessary to describe it by like explicit formula. If you just can describe, so it's unambiguously clear what this map is, kind of geometric. Like for example, like this stereographic projection, you can just describe how it looks.
Like for example, like for a torus, we know that from a torus we can construct a torus from a quotient by identifying the edge of the square, and then can I use argument something like from the square I remove a point at the origin, and then I deform it onto the boundary, and then when I identify the boundary, I get a bouquet of two circles intersecting at a point. Without providing any map, or I need to.
Well, you just need to. It's enough to describe geometrically, like what is the, like if you define some deformation reduction, you should describe geometrically what is the image of a point. I mean how.
Okay.
On this map, it's not necessarily to write explicit formulas, but just so it's from your description, it's clear what is a map.
Okay, so it's like, and for the last question, like so. By this, the Riemann surface of G and SG is like something like a torus of G holes, something like that, which we can construct it from 4 G cons. And then can I use just the same strategy as the previous problem, like removing the hole and the origin, and then I retract everything onto the boundary, and when I identify the boundary, I get the wedge of like a square. Circles, something like a wedge of the circle, something like that.
Yes.
Okay, so I don't need to write everything very formally and very explicitly.
Yeah, I mean, if you just can write, describe again geometrically, like where points move under this deformation retract, it's.
Okay, so if I try to solve, so I know I can somehow describe it by a picture how to do that, but I will try to write it analytically, but if the analytic part is wrong, will the answer consider okay if the geometric one is okay? Like,
Well,
I will try.
probably. Well, it's
Yeah. Okay. Oh, okay. I'll try to write it, and I will send you email again asking if it's the analytic formula, because I'm trying to write it now. Okay. Thank you, Professor.
okay.